Today, on Guess What I Found Out, we are going to talk about one of the most sinister, elegant, and frankly disturbing relationships in the entire animal kingdom. We are talking about a tiny metallic green wasp that turns cockroaches into compliant little zombies. Ladies and gentlemen, Curious George, meet the emerald jewel wasp, also known around here as the mind hijacker in a tuxedo. The emerald jewel wasp, Ampulex compressor if you are feeling fancy, is a parasitoid. Not a parasite, not a predator, a parasitoid. That distinction matters, and we will get there. She is a roughly 2-centimeter insect with iridescent green and copper wings, and she looks like someone bedazzled a tiny assassin. She is found across South Asia, Africa, and parts of the Pacific, and she has one goal: find a cockroach, do something horrible to it, and raise her babies inside it. The cockroach in question is the American cockroach, Periplaneta americana, a creature many of us have sprinted away from in a hotel bathroom. These things are fast, armoured, and equipped with one of the most sensitive early warning systems in the insect world. On their legs, they have sensory spines that detect the faintest vibrations and air movements. When something approaches too quickly, those spines trigger an immediate defensive kick. A cockroach can feel a threat before it can even see it. So how does a 2-centimeter wasp take down something 6 times her size with reflexes like that? She does it in 2 steps, and the precision involved is enough to make a neurosurgeon put down their coffee in quiet respect. Step 1. The wasp delivers a sting to the cockroach's first thoracic ganglion, which controls the front legs. The result is a brief paralysis, just long enough to keep the cockroach from kicking her away while she sets up her finishing move. It is like a bouncer being handed a drink before the real conversation starts. Step 2. She delivers a second sting directly into the cockroach's brain. Not near it, into it. Using sensory organs on the tip of her stinger, she probes around until she finds the right location, and she injects a precisely calibrated cocktail of venom that does something extraordinary. The cockroach does not die. It does not even lose the ability to move. What it loses is the will to flee. The cockroach just stands there. It could walk, it could run, but it does not want to. The wasp then clips the cockroach's antennae and drinks a bit of the hemolymph, which is basically cockroach blood, giving her a snack and leaving a shortened antenna she can use as a leash. She then walks the cockroach, like a dog, back to her burrow. If you're finding this absolutely unhinged, you are in excellent company. Stick with Guess What I Found Out, because we cover exactly this kind of beautiful nightmare every single week. Hit that follow button so you never miss an episode. Inside the burrow, the wasp lays a single egg on the cockroach's leg. She then seals the burrow and leaves. The cockroach sits there, grooming itself, completely calm, not attempting to escape, while a wasp larva hatches and begins feeding on it from the outside at first, and then from the inside. The larva is careful not to kill the cockroach too quickly, keeping it alive as a fresh food source until the larva is ready to pupate. At that point, it hollows the cockroach out entirely and emerges as a fully formed adult wasp. Now, here is where the science gets even more specific, and honestly, a bit more impressive. Researchers discovered that the wasp does not just use 2 stings. She also delivers a sting to the second thoracic ganglion, the one controlling the middle legs. This third point of contact was, well, unexpected and only identified through careful observation. Its purpose appears to be positional, helping the wasp precisely place her egg in exactly the right spot on the cockroach's leg so the larva lands in optimal feeding territory. Researchers also found that the wasp has specialized sensory hairs on her abdomen called setae that help her locate that precise egg-laying site. When scientists trimmed these hairs, the wasp still went through all the motions but consistently misplaced the egg. The larvae that hatched from those misplaced eggs did not survive. Those tiny hairs are not decorative. They are the targeting system. And this is worth pausing on, because it is the kind of discovery that only happens when someone sits down and watches something very carefully for a very long time. Not a dramatic moment, just a researcher noticing that the wasp kept doing something slightly unexpected at the second ganglion, and deciding to follow that thread. That kind of attention has revealed one of the most intricate host manipulation systems ever documented in the insect world. If you have made it this far and you are as fascinated as we are, go ahead and, well, smash that like button. It tells the algorithm that people actually want to learn things that are genuinely strange and wonderful, and honestly, it helps us keep making these videos. Now, let us talk about what this relationship actually means, biologically speaking. The wasp is classified as a parasitoid rather than a parasite because the host does not survive the interaction. True parasites keep their hosts alive indefinitely. Parasitoids use the host as a single-use resource. The cockroach, meanwhile, is not a prey item in the traditional sense either. It is not killed and eaten. It is kept alive, neurologically suppressed and metabolically drained over time. It exists in a kind of enforced calm that has no analogue in our own experience, but which tells us a great deal about how specific and targeted neurochemical manipulation can be. The venom that produces this zombification contains compounds that block octopamine receptors in the cockroach's brain. Octopamine is the insect equivalent of adrenaline. Block it, and you do not get an unconscious cockroach. You get a cockroach that simply has no motivation to initiate movement. Now, the cockroach is not sedated, and interestingly, it is not in pain either. Instead, what's actually happened is that its drive to escape has been surgically removed by chemistry. This rather peculiar phenomenon has, unsurprisingly, attracted serious attention from researchers studying neurological conditions in humans. Because, you see, understanding how specific receptor systems govern motivation and the initiation of movement has implications that stretch well beyond the insect world. And here is the thing that keeps scientists coming back to this particular relationship. Almost every aspect of it turned out to be more specific, more targeted, and, well, more surprising than initial observations suggested. The three-sting sequence was not assumed from the beginning. The sensory hairs on the abdomen were not obvious. The precise role of the second thoracic ganglion only revealed itself when someone looked closely enough. The more carefully researchers examined this interaction, the more layers of sophistication they found. That is the part of this story that applies far beyond entomology. The emerald jewel wasp has been known to science for a long time, but what it was actually doing at the level of neurological targeting and sensory guidance was hiding in plain sight, just waiting for someone to pay close enough attention. So here is your question for the week. Curious George? Given that the wasp leaves the cockroach alive and aware, but unable to flee, do you think the cockroach experiences anything during that time? Is there a version of suffering happening, or is the removal of the escape drive also a removal of the subjective experience of danger? Drop your answer in the comments below and tell us your reasoning. There is no wrong answer here, just a genuinely interesting question. If you want to keep exploring the parts of the natural world that are equal parts beautiful and deeply unsettling, subscribe to Guess What I Found Out. We find the things that make you stop and say, wait, that is actually real, every week without fail.